Have you ever wondered, what if we could power the world using the same force that powers the sun? Not just solar energy from panels. I mean, actually recreating the sun's energy here on Earth. Tapping into the very reaction that lights up our sky, drives the weather, and gives life to our planet. That idea has a name: nuclear fusion. And if we ever get it right, it could change everything. Our electricity, our climate, our global economy, even the way nations interact. But there's just one catch. We've been chasing fusion power for more than 70 years, and yet, your house isn't running on it. So what's taking so long? And why are scientists and billionaires still betting everything on it? Let's explore. So, first off, what is fusion? At its core, fusion is a nuclear reaction. But it's not like the kind that powers today's nuclear plants. Today's reactors rely on fission, splitting large atoms like uranium to release energy. Fusion does the opposite. Fusion means joining. Two small atoms, usually hydrogen, collide and merge into a single, larger atom. Most commonly, they form helium. And in the process, a tiny bit of mass is lost. But thanks to Einstein, we know mass isn't really lost. It's transformed. E equals mc squared. That tiny bit of mass becomes energy, a lot of it. This is how stars work. This is how our sun has been burning for over 4 billion years, by fusing hydrogen into helium. In fact, just one fusion reaction releases about 1,000,000 times more energy than a typical chemical reaction, like burning coal or gasoline. And here's where it gets even better. The fuel for fusion? It's hydrogen, the most abundant element in the universe. You can extract it from water. Yes, ordinary water. A few liters of seawater contain enough hydrogen to power an entire home 4 days. There's no carbon dioxide, no smoke, no soot. And the waste? Mostly harmless helium. Compared to fission, fusion is a dream. Fission produces long-lived radioactive waste. Fusion doesn't. Fission can melt down, fusion can't. Fusion doesn't just offer energy, it offers clean, safe, and abundant energy. But if it's so great, why aren't we using it? Because making fusion happen on Earth is incredibly, incredibly hard. You see, atoms don't want to fuse. They're positively charged. And like charges repel each other. It's like trying to push two magnets together the wrong way. They push back. So how do you force them to fuse? You give them enough energy to slam into each other so hard they overcome that repulsion. In the sun, that happens because of its immense gravity. Millions of tons of pressure crushing atoms together in its core. But we can't recreate solar gravity on Earth. So we do the next best thing. We use heat. A lot of heat. To make hydrogen atoms fuse, you need to heat them to over 100 million degrees Celsius. Yes, hotter than the core of the sun. At that temperature, matter becomes plasma, a superheated, electrically charged gas. It glows, it swirls, it behaves like a living thing. But plasma has one big problem. It can't touch anything. It would vaporize any material known to man. So how do you hold a sun-hot plasma without a container? The answer: magnets. Specifically, magnetic confinement. Imagine a donut-shaped vacuum chamber surrounded by giant superconducting magnets. That's a tokamak, one of the main types of fusion reactors. It uses magnetic fields to suspend the plasma in midair, away from the walls, so it doesn't melt the machine. It's elegant and incredibly difficult. Because plasma is unstable. It wriggles, it twists, it wants to escape. Keeping it under control is like trying to hold a fireball made of jelly, using only invisible magnetic hands. There's also another approach: inertial confinement. Here, Scientists use lasers, really big lasers. They fire dozens or even hundreds of beams at a tiny fuel pellet, compressing it so rapidly it heats up and fuses for a fraction of a second. This method is incredibly fast and violent, but also very promising. Both approaches, magnetic and laser, have their strengths, and both are being pushed to their limits. So, who's working on fusion? A lot of people. Let's start with the big one. ITER, in southern France. It's the largest scientific collaboration on Earth. Over 30 countries are building it, including the US, China, Russia, the EU, and more. ITER is a tokamak, a giant one. Once it's complete, it will attempt to produce 10 times more energy than it consumes. Then there's JET, the Joint European Torus, based in the UK. JET has set numerous records and paved the way for ITER's design. In the US, the National Ignition Facility uses lasers, not magnets. In 2022, they reached a historic milestone. For the first time ever, a fusion reaction produced more energy than was put into the fuel. That moment, called ignition, was like lighting a match that burns brighter than the spark that started it. It was a breakthrough. But there's a long road from breakthrough to power plant. And that's where the private sector comes in. Startups and companies are jumping into the fusion race, armed with new tech, fresh ideas, and billions in venture capital. Commonwealth Fusion Systems, spun out of MIT, is building compact tokamaks with next-gen magnets that could shrink reactors dramatically. TAE Technologies is using beam-driven fusion, aiming for cheaper, scalable reactors. Helion Energy plans to deliver electricity to the grid by 2028. That's just a few years away, and dozens more are emerging, each with a different design, a different roadmap, but the same dream. Fusion isn't just science now, it's a business, a race, a global movement. So why does it matter? Because fusion could solve multiple crises at once. We're facing a climate emergency. We need to cut carbon emissions, fast. Fusion produces no carbon, none. We're facing energy insecurity, fuel prices spiking, wars over oil, fragile grids. Fusion uses no fossil fuels, no pipelines, no mining, just water. We're generating more waste than we can store. Fusion produces almost no long-lived radioactive byproducts, and most of all, we're using more electricity than ever. Electric cars, AI server, data centers, air conditioners. As the world electrifies, we'll need more power, not less. Fusion could provide that power, reliably, safely, and at scale. It could bring electricity to rural villages without needing massive infrastructure. It could decouple energy from politics, putting power in the hands of everyone. And maybe, just maybe, it could power spacecraft. Fusion's energy density makes it ideal for long-distance missions to the Moon, Mars, and beyond. Fusion isn't just about science. It's about climate, equity, and the future of civilization. So, when? When does fusion stop being the energy of the future and finally become the energy of now? It's hard to say. Some say 30 years, some say 10. The truth? We are closer now than we have ever been. Breakthroughs are happening faster than ever. Superconducting magnets, artificial intelligence-assisted control systems, new reactor designs. And yes, billions of dollars are being poured in from governments, tech giants, and visionaries who believe it's finally time. Fusion won't solve everything overnight. It won't replace solar, wind, or even fission right away. But it could become a pillar of a future clean energy mix. A stable, reliable, base load energy source without emissions or waste. And here's the wild part. We're not talking about centuries. We're not even talking about far-off science fiction. We might just be the generation that unlocks the power of the stars. Until then, fusion remains the future.